Hello everyone. In this video, let us do some math. Let us do some amount of derivation in this particular video. So we identified the drain current as the product of velocity of charge carriers multiplied by available charge over the channel width, and this was the theoretical explanation for the drain current. Okay, so what we have to do is we have to come up with a model, come up with an equation for ID that can be very well used by the SPICE engine. Okay, so SPICE engine already has some complicated and some accurate equations or models for drain current. We will be looking into one such simple model. Okay, so let's try to come up with some model, and that will help us to understand the basics that goes behind SPICE simulations. Okay, so let's start with that. So we will do some amount of math, some derivation, some integration, and all these things. Okay, so we have this channel width complete area, which is the gate overlap area over the source and drain. Okay, and the drain current, as mentioned in this theoretical expression, it's a product of charge carriers and the available charge. So velocity is Vn of x. Let's denote velocity by Vn of x, and the charge is defined by Qi of x, which we just derived at this point. Okay, so with that said, let me try to tell you what is Vn of x. So velocity, take this handy equation from it's a product of mobility and electric field. So it basically says that if there is a variation in this small dx over the complete channel length L, in this small dx, if there is a change in the distance, there in this small dx there is a change in the potential, there's a change in the voltage, because we discussed some time back that this is a potential gradient. Okay, so in this case, over a small distance of L, there is a change in the voltage, and as a result of the change in the voltage, your velocity differs. Okay, so that's why velocity is proportional to the electric field, and the constant is denoted by mobility, and mobility is constants for electrons and holes for charge carriers. So velocity will be given by mu1 into dv by dx. So dv by dx is the one which I was mentioning, that in a small distance across the complete L, there's a small change in voltage, and with the change in voltage, your velocity changes. So we have got two equations to substitute for this drain current. We have velocity, which can be taken it from here, and we have this Qi of x, which can be directly substituted over here. Okay, so then the next job is to substitute and integrate. So we will substitute Vn of x, we'll substitute Qi of x, and integrate it across the complete channel length L. Okay, so there are two areas that we need to integrate. So we have two varying items. We have dv and we had dx in this particular expression. So dv is changing from 0 to vds, because that's the highest voltage that we can attain, and dx is the length varying. So across this complete length, you have the voltage varying from 0 to vds. Okay, so dx has to be integrated till 0 to L, and dv has to be integrated from 0 to vds, because that's the maximum voltage that it can attain over here. So let's integrate it, and let's identify a working model as the simplest working model for drain current. Okay, so this is where we substituted. We have Vn of x, Qi of x into W, because it has to be done over the complete channel width. So Vn of x is mu n. So it's basically a pure substitution integration. Some math, we'll be trying to do some math in this particular video. So you have mu n into dv by dx into Cox, basically the substitution over here, Cox vgs minus vdx minus vt into v. Okay, so the next job in the integration is to take the dx in the left hand side, keep the right hand side equation as an expression, as a function of dv, and we'll try to integrate this. So once you try to integrate dx, you from 0 to L, the integration of dx will be L. From 0 to v, the integration of dv will be vds. Okay, but you have this v term over here, which is a function of x. So let's try to integrate it. I've done it already, and you will have to just look into some handy equations over here. So this is what we get after integration, and after integrating it completely over the channel length and the complete voltage. This is what you get. You get a drain current which is mu on Cox W by L, and this is all constant. These are all technology constants. And since these are constants, this will be called as technology parameters or models for model file. So this will be, you need to supply the values for Cox, or basically Cox is epsilon ox upon Tox. I'll come to that. So you have to supply those technology constants to your SPICE simulations, so that SPICE will use these values and compute the drain current, and that will be your SPICE engine, and that will be the job of a SPICE engine. Okay, then you have VGS minus VT into VDS minus VDS square by 2. This equation still looks a bit lengthy for a cutoff region of for a linear region of operation, because when we say it's a linear region of operation, we should see the equation to be a linear function of the voltage, especially VDS. But over here you see it's a linear function, or it's a quadratic function of VDS. It's VDS square by 2. So let's try to simplify this even more. Okay, and these are for voltages which are these are for VDS voltages which are less than, which are very less, it's like 0.05. Okay, and we'll eventually come up with a condition that what value of VDS it should be to be it in the linear region. Okay, we'll come to that. So we have just substituted mu and Cox by a constant. It's called Kn dash. It's again a process transconductance. This again becomes a constant. So this again becomes a model file. So whatever over here, if you see, this is the model for this particular MOSFET, and you need to provide model parameters. There are some it's called a model file. You need to provide some model parameters to your engine, so that the SPICE engine computes ID accurately. Okay, and these are all technology constants. You just pick up a technology node and you'll get all these constants from that particular technology node. I'll come to that when we do the SPICE simulations. Okay, so this term is referred to as process transconductance, and your drain current equation now becomes Kn as VGS minus VGS Kn VGS minus VT into VDS minus VDS square by 2, and where Kn can be again even substituted by Kn dash dot Kn dash into W by L, which is again called your gain factor. This is one more constant, one more technology parameter. Okay, so this one looks much cleaner than this one because we have substituted this complete constants by a single constant. So this looks much cleaner, but still we have not come to a point where we say that it's in the linear region, because your drain current is still a quadratic function of VDS. So let's try to do some more math over here. So we have these values. Okay, let us clean up everything. So we have these values. Okay, we have this drain current equation. We'll try to substitute these values in this drain current equation and see what we get, and see if we can derive something out of it. Okay, so let's do that. We have VGS as 1 volts. We have your threshold voltage VT as 0.45 substituted over here. You have your VDS as 0.05 minus VDS square by 2, which is 0.05 square by 2. Okay, if you try to go ahead, it looks something like this. Kn, your drain current is the constant, the gain factor. Compute this one and get 0.0275. For this one you get 0.00125. So one thing to notice over here is, if you see this particular term is very close to 0, and it's almost close to 0, so you can actually neglect this term, and it's 0 for it. It's basically true for all values of VDS which is less than VGS minus VT, and that brings us to the condition of linear region. So whenever your VDS is less than VGS minus VT, your MOSFET operates in the linear region. Okay, so now when you try to remove this term, when you try to remove this, equate this to 0, so what basically are we doing? We are trying to equating this complete term by 0. So VDS square by 2 will be now approximated to 0 for all values of VDS which is less than VGS minus VT. And now if you try to come up with the equation for your drain current, it's Kn into 0.0275. Basically 0.0275 is nothing. It came up from VGS minus VT into VDS. Okay, so once we try to substitute it, it's ID equal to Kn VGS minus VT into VDS. Now it becomes a linear function of VDS. Okay, and this goes in par with the explanation that we said the MOSFET operates in the linear region. And the reason is purely simple, because for all values of VDS which is less than VGS minus VT, this brings us to a very good model for ID, which says that for all lower values of VDS, or for all values of VDS which is less than VGS minus VT, your device operates in linear region or resistive region of operation. And this is the model. This is a very basic, very simple model for the drain current in linear region. Okay, so with that said, we need to expand, we need to do some more math. So how do we do it? Basically what we'll do, we'll take some more values of VGS and try to plot drain current for different values of VGS. Okay, and that's where you need an engine, you need an automated system to do it, and that's where SPICE comes into picture. So I'll come to that point. So let's try to, I need some more minutes on the how does this SPICE evolves and all those things. So let's try to continue from this point in the next video. Thank you.